For this lesson, we're going to talk about a different type of recurrent neural network, one that's called a long short-term memory. Notice where the hyphen is. It's between the short and term. Long short-term memory. It's not long short-term memory, anyway, or LSTM. So the goal is to see a common type of recurrent network and understand what its advantage is. So, as we talked about before, the benefit of a recurrent neural network is that it can accumulate a hidden state that encodes input over time. So, for example, a properly trained RNN could complete the sentence, "To ride a bicycle, put your feet on the pedals." Now, that's great. Now, imagine we had a slightly more difficult passage where context was sort of over a longer span of time. However, one difficulty with an RNN is that it can be very difficult to train it to maintain information in its hidden state for a long time. It would have trouble completing this paragraph. A bicycle is an efficient mode of transportation. It was invented in blah, blah, blah by whomever, and it's used a lot in Europe, and it's good for your body, get lots of exercise. To get started, pick one up and put your feet on the... Now, notice in that last sentence, there's no mention of bicycles at all. You'd have to know what the context of the paragraph was from previous statements. So you'd have to maintain more stuff in memory for a longer time. So this was shown to be quite difficult with an RNN. So the instability was first pointed out by Bengio et al., Joshua Bengio et al. In 1994 in this paper. Learning long-term dependencies with gradient descent is difficult. They showed that the longer you need to keep information in memory, the harder it is to train. The backprop through time algorithm becomes unstable because of exploding or vanishing gradients. So let's take a bit of a closer look at that. So here's an unrolled neural network. Now let's look at computing I would actually now write this like this. If we were to compute that, we could write it the gradient of E with respect to HI in terms of the gradient of E with respect to HI plus 1. And in fact, I'll just go ahead and write the formula down. Okay, so that's great, but I could notice that there's this thing here, so I can also expand that and write it in terms of the gradient of E with respect to HI plus 2. So I'm going to rewrite that whole thing. So plus some other stuff. There are some cross terms here because there's a part in here that has V transpose in it as well, which I sort of took out and I put over here just to kind of show this leading term. So there's other stuff. So if I continue that process and unpack all those gradients of E with respect to the different I's all the way up to the end of the unrolling sequence, the leading term will look like this. So I'm actually, there are a whole bunch of different products here. Some of these are Hadamards and some of these are not Hadamards. I'm not going to sort of dissect it to that level of minutiae. But you can see that it's a whole bunch of sigma primes times connection weight, sigma prime connection weight, sigma prime connection weight, just like we had before with the vanishing gradient. So it's this kind of product that contributes to the vanishing and exploding gradients. Okay, so what are we going to do to get around that? LSTM, long short-term memory. To combat this gradient decay, Hochreiter and Schmidhuber in 1997 proposed an additional hidden state that persists from step to step. It does not pass through an activation function or get multiplied by the connection weights at each time step. So it's kind of an internal thing. It sort of follows, it gets recycled, but following a different path. It doesn't kind of exit, if you like, it doesn't kind of exit the cell and come back in. It sort of stays internally, so it doesn't fall victim to being shoved through this activation function every time step. So in a drawing, this is a standard RNN. And you can see that the hidden state gets recycled with this connection, this recurrent set of connections here. On the right here, I'll draw an LSTM, long short-term memory. So it looks kind of the same so far, but the internal state I'm calling C. Now, there is this way to recycle C and bring it back, and this is H, so I sort of a decoded hidden state we call H, and it does have connection weights W. But also this hidden state C has a way of sort of internally copying itself. So first of all, there are kind of different ways to control the flow of information. First of all, there's an input gate. So there's a way that we can allow X in, or X and H in, or we cannot. We could just leave C by itself. There's also an output gate, which controls whether or not our internal state gets sent out through the output paths. There's also an internal forget gate, or as you'll see, I'll call it a persistence gate, really. It's a sort of internal copy. And if the internal copy doesn't get done, if it doesn't get copied, the internal state essentially gets forgotten. So that's basically what an LSTM is, and I'll start writing down formulas for all these different things. So you'll see that at the input gate, coming in from the bottom, there are two different things, H and X. X is like the input from the sequence, and H is kind of a recycled, decoded, recurrent connection. So they can work together and interact in various ways. H and X can increment C. At the input gate, H and X can erase C. This is the forget gate. And you'll see how later. And H and X can control the output of C. Okay, so putting it all together, we get this picture. So this is taken from this link down here. So it's just kind of a drawing. This whole sort of rectangle is one LSTM unit, but it's got many neurons in it, many different sets of connection weights and biases, and many different sets of kind of different layers of neurons. So let's just look at this a little carefully here. Everything in orange is what they call a layer. And these lines are basically showing the path of data, or sort of projections of information. And then the yellow circles or ovals are pointwise operations. So basically sort of Hadamard type or monomial functions. So you'll see here, if you were to put this into an unrolled backprop through time context, we're going from left to right, and you can see that the internal state C sub t minus 1 from the previous time and H t minus 1 are coming in from the left, and they're interacting with stuff, and then they're going out through the right. Okay. Now there are these different gates here. So here's what I'm going to call the forget gate. This will be F, maybe I'll do orange. F sub t. It's the forget gate. This here is the input gate, I sub t. And over here is the output gate, O sub t. In general, it's not a good idea to use I or O as variable names. Avoid that. But that's commonly used in this context, so I'll use it anyway. Okay. Now each of those orange things is actually a whole connection. It's a whole population of neurons with a set of connection weights and biases, input, then passes through an activation function. So you can think of each orange thing as a full layer in a feed-forward network. A quick joke. We were driving one time and my friend asked me, "Have you ever fallen asleep while driving?" And I said, "No. I've woken up while driving though." First, the forget gate, it's actually a non-forget gate, or what I like to call a persistence gate. Persistence gate. So f sub t is the value of the gate. It's going to be between 0 and 1. If it's 0 or 1, those are kind of the opposite extremes of the forgetting or persistence operation. So it's going to be run through a logistic function, which will give something between 0 and 1. And it's going to be, what are the inputs here? So we're talking about this thing here. No, I don't want it that way. I want it this way. So we're talking about whether or not information passes through there, whether or not C, to what extent C gets copied over and persists inside. So that gate thing is here. It's got two different inputs, ht minus 1 and xt. So that's why we have t minus 1, xt. I'm using subscripts now for steps in time, times wf, connection weight matrix, plus the bias for the forget gate. Okay, so if this gate equals 1, that means persist. If it equals 0, forget. And you can see why, you'll see where that comes into context later on. Will you? Yes. You'll see that this gate gets multiplied. The value of this gate multiplies the ct minus 1 and gets added to the ct. Now the internal state for the next time step. Okay. Now, similar story for the input gate, really. The input gate is here. So we're going to determine to what extent the information gets through that gate. So the input gate is logistic, again, ht minus 1, xt. This is basically taking the h and the h from the previous time step and the x is the input to this time step, creating one long input vector. That's being multiplied by some connection weight matrix, wi, and plus some bias for the input gate. So if it equals 1, that means input. If it equals 0, that means don't input. That means we're not going to increment the internal state with whatever's traveling along this path. It all looks very confusing. I think what happened is, it is kind of confusing, except once you have automatic differentiation, you can just put a bunch of pieces together and use autograd to do backprops. So it's not that hard, really. Okay, so what is the input? What is this last arrow that I drew that goes up through the hyperbolic tangent function? Well, that's just c sub t tilde. So that's following along this path. And it's hyperbolic tan of, again, ht minus 1 xt, this sort of concatenated input, times set of connection weights and a bias. Okay, so that allows us to take the h from the previous state and the current input and morph it into some useful representation that we want. Okay, so combining now those two, so we've got this coming along here, we've got this coming up here, and we're going to add them to get our new internal state. So it's the forget gate times Hadamard times ct minus 1 plus the input gate Hadamard times ct tilde. So we're taking our old internal state, incrementing it with our new sort of input stuff, and combining those with a combination of with the forget gate and the input gate. Okay, then finally there's the output gate. That's this one down here. Whoa. The output gate. So whether or not this connects to the output. And it's the same pattern as before. And if it equals 1, that means output. If it equals 0, no output. And what is the actual output? Well, the actual output is h of t is the output, the value of the output gate, Hadamard times hyperbolic tan of ct, the current internal state. Of course, you could if you wanted to have another set of connection weights and biases, whatever. So after all that, what have we got? So ct equals, let's see, first is the forget gate. So sigma, now I'm just going to say x at time t is kind of the combined h and x, okay? So it's x from time t times the forget plus the bias times the previous internal state plus the input xt input plus bias input times hyperbolic tan of okay. So we'll come back to that later, but in particular in reference to this term here. So going from one step to the next, our internal state really just gets multiplied by the state of the forget gate. So weight matrices, as you probably saw, we have the WF here, WI here, and WO here. Oh, this is WC. This should be WC here. Right, okay. Okay, so how does this make a difference? How is this particular setup helping us? Well, I just alluded to it not long ago. The CT, the internal state at time t, is the forget gate for that for that time step times the previous time step plus an input at time t, Hadamard times ct minus 1 tilde. So I'm really focusing on this first step. So how does the gradient of E with respect to c t minus 1 depend on the gradient of E with respect to ct? So as we're doing backprop through time, going down our time steps, the question is, how does the gradient from one time step, what happens to it when you go a step further down? So the gradient of E with respect to ct minus 1 equals the gradient from above, Hadamard times the forget gate plus other stuff. So as each step you go, you're multiplying by that time step's f, forget gate. Now that f could be 0.5 or could be 0.25, it could be something small, but it's a lot easier for those forget gates to be closer to 1 or closer to 0. Well, if it's close to 0, you've forgotten everything, which is actually a feature. If you want to, partway through a sequence, forget everything, then that's the network's prerogative, right? And you shouldn't push a gradient down through a forgetting event. But if it's trying to remember this stuff, then you want to maintain those gradients as you go down through the time steps. So it's a lot easier to make that forget gate equal something close to 1. And as you work your way down, those things close to 1 don't affect you as much as it would be like a logistic function where it's the maximum slope is 0.25. So as long as f is close to 1, there's little decay of the gradient. So this is LSTM. This is one version of LSTM. There are different versions of LSTMs. You can imagine putting different gates. I already alluded to one before where you could have yet another layer of sort of output re-representation or transformation before you give your output, the H. Like you could, as I said, you could have another layer thing here that transforms again. And you could combine things and mix things. You could say that maybe the forget and the input gates are have to add up to 1. So the more you're forgetting, the less you're inputting, or the less you're forgetting, the more you're in. Did I say it correct? The more you're forgetting, the more you're inputting. Yeah, that makes sense. I think you get the idea. There are simpler versions of this called GRUs, gated recurrent units. So there's all sorts of different things you can do with these. The take-home message for these types of things, though, is that there's this internal state that gets copied with fewer non-linearities in between from time step to time step. Long short-term memory. Before I let you go, I just wanted to very quickly go over the different types of memories, memory systems that you have, or that all mammals have. You basically have 3 different memory systems. The first, and the reason I bring this up is because you might have heard of long-term memory and short-term memory, and here we are talking about long short-term memory. So they're not necessarily related to our long-term and our short-term memory, but it's interesting to learn something about your memory. You have 3 systems. The first one, let's say, is the shortest and is called working memory. It's like if you're remembering a phone number or the price of something, and if you keep repeating it to yourself, it sort of stays in your mind, like $31.97 or something, $31.97. But as soon as you get distracted, you forget that number and it's gone. That seems to be implemented in the collective activity of populations of neurons. As long as they're maintaining their firing pattern, you can remember that. So that's working memory. The next level is what we call short-term memory. It's actually longer than working memory. And it's the sort of thing where you can remember what you ate for breakfast this morning, or what you, maybe what TV show you watched yesterday, or some news item. It's kind of like in the 24 to 48 hour time span. And that seems to be implemented in your hippocampus, which is it's a medial temporal lobe sort of thing. It's kind of inside it doesn't really matter where it is. But it's a special part of your brain that seems to be important for storing those types of memories. They're stored basically by changing sort of the efficacy of the synapses and the neurons. So it's not the activity of the neurons that's storing the information. It's kind of the short-term changes in the sort of excitability of the synapses and the neurons. And so those can maintain those memories for kind of a 24, 48 hour period. Now, it seems that what happens when you're sleeping, and maybe when you're dreaming, is that some of those memories get encoded into long-term memory. Long-term memory is things like remembering your parents' names, or your birthday, or events that happened when you were a child, or even events that happened a year ago, or even a couple of weeks ago. Those types of memories get encoded it seems to get encoded in the actual wiring, the connections between your neurons in your cortex. So the outer noodly folded layer of your brain is your cortex. The connections between those neurons seem to be what encode your long-term memories. So that's kind of like changing the connection weights and biases in your cortical neural network. So there you go. Working memory, short-term memory, and long-term memory.